I don't know if this lighting level is better or worse, but this is it or bright. Not like anything between the two. And it's sort of like, having a stereo system that has a little too quiet and really loud. Let's get going. I think that actually is a real UBC clock because it is exactly on time, synchronized. Today is September 28th. I think I kind of played a dirty trick, which was I had originally said that I was going to do 9 and then 14, and somewhere in my head I convinced myself I was doing 14 today. And about the time I realized that it was supposed to have been 9, I was like, I've set everything up for 14. I can't go back and change it. So it's not that if you read chapter 9 instead of 14, then I apologize, but that means next week will be easier. In some ways, I think that this is better because it gives you a longer period of time to go over 14. Because I'm guessing that most people don't read until after the conversation, the discussion here. I don't know. How many people read the reading before the class? How many read it after the class? You're allowed to say both, of course, obviously. And how many of you don't read it at all? Wow. Everybody reads it. Good. I actually like the Petrov book. I think it's pretty well written. But it's not a textbook, or it's not a typical kind of textbook. Oh, yes, the boring logistics slides, yada, yada, blah, blah, blah. Yeah. Let's. Why is this slide? Now, what's really weird is here and say, no, I updated these slides. So I guess next week is, okay, that's right. Next week is Tuesday, October 3rd. Will be the self-assessment is due for the discussion that we're having today about chapter 14. Then your design feedback is also due on Tuesday. So you should have been assigned. It looked, when I looked earlier, it said that everybody got 3 assignments to review. Do you have a question about that, or? They should be on Canvas. It should be under the design project section where you submitted it. It should then show you the 3 that you're supposed to review. Oh, great. So it's sort of like, those web pages you go to where the important stuff, the button you have to click on to get what you want is below the fold, and you don't realize it until you scroll down. I hate that design. It drives me crazy. You just write up notes, I think. I haven't used it, so this is interesting. One of the things I've learned is that what Canvas shows me, even in the student view, isn't what it shows you. It's like people complaining they couldn't see the quizzes anymore. I'm like, I don't know why not. I have the always show quiz button, but apparently once the quiz expires until it's graded, it won't show it to you. I've graded them all, and hopefully you can now see them again. So don't trust me when I say what's going on there. There should be a mechanism for providing feedback there, though, if I've set it up correctly. It's also possible I've done it wrong, in which case we'll fix it and it won't happen again. Let's see. There's also going to be a post-lecture self-assessment activity on Thursday. That will be for the Tuesday discussion. That will be about Chapter 9. Chapter 9 is a lot lighter than Chapter 14. A lot lighter. Chapter 14 is incredibly dense as I was sitting there saying, you know, I talked about Paxos and Raft and view stamp replication and quorum consensus, all in 4 separate sessions. Here, we'll just cram it into one. And I'm going to see how that works. It's kind of interesting. There's a lot of similarity between these things, and in some ways, it may be better to talk about them more generally. One of the things I added today, I'm going to spend a lot more time talking. I have more slides than I usually do today. One of the things I actually did was I wrote what I think will be very helpful in understanding the general model of consensus, which is what does it mean to have a quorum? There are a couple of students who actually haven't been submitting the self-assessments. I haven't reached out to them yet, but don't be that person. They're probably not in the room. They're probably not going to watch the stream. They probably won't watch the YouTube videos. Last term, I had one person who failed, and that's because I sent them a note and I said, if you take the final, you'll pass. And they didn't take the final. I mean, literally, I said, you know, you're right on the edge. All you have to do is come in and take the final and, you know, randomly choose some questions and you will pass. And they didn't. Today's failure example is one that I used last term, so I'm just recycling here. It is a Microsoft Azure out failure. What's interesting about it is I love how they don't really tell you exactly what things mean, but like they say that, you know, it impacted Microsoft 365, which means that people couldn't read their email. They couldn't use their documents online. They couldn't use SharePoint. They couldn't get access to their storage. Microsoft Power Platform is this big data analytics package that businesses use. Oops, that's not a good thing to have offline either, is it? Azure Government, which means you've now got the government pissed off at you as well. These are not the kinds of bug reports that you want to have coming across your desk when you're working at Azure. I don't know, is anybody thinking of working at Microsoft? Turns out the CTO of Azure used to work for me years ago. So like when I went and was doing this 3-month gig at Microsoft Research, they were like in awe that I knew Mark Rusinovich, who's the CEO. I'm like, yeah, he used to work for me. He used to work for you? Yeah. So I sent him emails and just telling him what was going on. And it was very interesting because he was interested in the project we were working on. Why did it happen? It was a wide area network reconfiguration event. It doesn't have anything to do with the data center in this particular case. It had to do with the network. Networks fail. The change command, I just love the wording here. It's so carefully wordsmithed. It had not been vetted. I'm sure that the actual words that someone used when they were describing this, when they first figured out what happened, were not nearly so polite. Right? Who wrote this command? It didn't take them too long to recover the network, only about a half hour. What time did it start? 7:05, 2 hours, 2.5 hours. So 2.5 hours, they've got the network back. But then, of course, the problem is that some other stuff that automatically is supposed to preserve the health of the network went wrong. These are the kinds of failures that we see in the real world. They are complicated. We're talking about simple failures like, well, gee, one of these servers goes down, and what's going to happen? How are we going to get that switched over from our primary to our replica? And this is stuff where, hey, the network keeled over dead for 2.5 hours, came back up, and some other automated process had shut down, and things weren't good, and it wasn't healthy. So we're scratching the surface. Things get a lot worse underneath. Had to manually restart systems. It's not quite as bad as the Facebook outage where they had to actually send people to the data center to manually restart the systems. They were able to do it remotely, but still, that's a pretty serious thing. And it inspired today's t-shirt, which is, you know, if I'm on life support, just unplug me and plug me back in and see if that helps. Because that's what we do in systems. The whole thing is a blog post from last January. It's very interesting if you want to learn more about it. I find the failures help people understand why this stuff is real. These are all distributed systems. These are all aspects of distributed systems, things that actually fail in ways that we didn't really understand they could fail in. So no matter how many failure conditions you can think up, the real world will give you some that you didn't. So what did I want you to get out of Petrov chapter 14? I wanted you to learn what a quorum is and how it helps with consensus. In fact, I think that probably that is the most important concept to get in general from all of the distributed algorithms we're going to be talking about. How do I find a quorum? See, when we did the design project 1, we just had a primary and a backup. All we were doing was just an automated backup recovery system. It really wasn't that complicated. As we scale up, a simple way of doing that is we just simply add more backups. But it becomes increasingly expensive for us to coordinate between all of our backup copies. Because what we end up doing is needing to have, instead of 2 systems agreeing, 20 systems agreeing. Have you ever tried to coordinate, dinner planning for 19 of your closest personal friends? It's worse than doing it with 3. It just takes longer. Everything takes longer. So now we have a performance problem. So how can we mitigate that? Well, our goal in using replication was to provide us with a form of failure recovery. Can we come up with a form of failure recovery, of backups, that doesn't require that everybody have a complete identical copy of the data at every moment in time? And the quorum is going to be the way we're going to get out of this. So that's why it's really important to understand this, because this becomes the tool that gives us scalability. It's not 100% scalable, but it's definitely better than waiting for everyone in the room to agree. So what does consensus give us? It gives us a single agreement on a particular event or value. Now, the language they use is normally we've agreed on a value. But we can iterate over this. We can agree on a series of values. One of the benefits of having a log of operations is it defines an order of events. I've already mentioned, and we've talked about, the fact that you can change the order of some of those events and it won't make any difference to the outcome. So we could be flexible about our log and say that as long as it is isomorphic, that is, the operations may have been processed in a different order, but the results were the same, it's okay. I'll still consider it to be the same log. It's not identical, but it reaches the same endpoint. In consensus, that means we agreed on the same values. That no matter what order we processed those things in, we got to where we needed to go. And that's really what we're going to try and do. And we are going to need that because when we go to a quorum, that means not everybody even knows what the value is that we picked. So we have to start reasoning about this and say, how am I going to get back to a point where everybody has a copy of that value? This optimizes for the common case. And in the common case, nothing fails. It's really easy to build a piss-poor performing distributed system that has strong consistency because it compromises the performance of the common case when everything's running fine to protect you against the rare case. So this is another subtle challenge. We have to be able to do this in a way that has minimal cost. Now, minimal is very hand-wavy there because it very much depends upon how important the consistency is here. And we're going to end up looking at models where, eventually it'll be consistent, which means it's never actually consistent, but if we worked really hard, we could make it consistent, and that's close enough. And it turns out, for most of the things we do in the real world, it actually is close enough. We're going to talk about commonly used consensus algorithms. A lot of the differences in these consensus algorithms relates to the way they perform recovery. Their logs are different. How they reconcile their logs are different. What they do when a node falls off the face of the network is different. But the basic underlying process, which is how do we achieve a quorum, ends up being the same. We're going to talk about atomic broadcast, which is one of the strongest guarantees of the consistency protocols. It's not really good if you're trying to do high-frequency operations because it's very expensive. It does achieve very strong consistency, but it does so with not great performance. If you've got 5 operations a second, fine. This is a perfectly acceptable protocol. If you've got 30 million operations a second, it probably isn't going to work. How are we going to get somewhere in that range between 5 and 30 million? Where is that cutoff line? And this is a huge design space. This is a very large space of different approaches that we can take for solving this problem. How do we achieve a quorum? How do we agree on what happened? And then I threw in some examples of consensus used in real-world distributed systems. And part of my motivation for doing that is because you're probably already starting, well, you should be, starting to think about your capstone. What am I going to do? So I'm going to be talking about real-world distributed systems because I'm going to keep throwing out some suggestions of things you might want to consider. It's your project, not mine. If you can convince me that it's a bona fide distributed systems problem, go for it. And I'm pretty open to almost anything. If you're more like, I have to do this because I have to get something better than a 55, and it's easiest if I just take some idea that I know that the prof is going to accept, that's fine too. I have no problems with that. I don't expect that what you build in your capstone is going to make any difference. I have a hope that it will, but I don't expect that it's going to make any difference. It's going to be a piece of student code that no one's ever going to actually use or look at. But you all have the potential of doing more than that. And one of the ideas I'm going to throw out there is and some of the ideas I'm going to throw out there are things that could actually have more general use. You know, Linus Torvalds didn't really know very much about operating systems when he set out to build his own OS. Maybe you're the next Linus Torvalds. All right. What is a quorum? And I really thought about this as I was putting these slides together. This is actually the last slide I wrote, and I was like, I like the way this comes out because it doesn't go through the historical perspective on this. It goes straight to the meat. What does it mean to have a quorum? A quorum is given a set of servers, nodes, whatever you want to call them. We take a subset of those, and they all agree on the outcome. They all agree on a value. If it is a quorum, if and only if any other subset has at least one member that is in common. What that means is I cannot partition these servers up in a way that gives me 2 different outcomes. Now, the easiest way to think about this is we are going to wait until everybody has their values, and then we will know that we've got our quorum. But that's not necessary. That's much stronger and much more expensive to accomplish than what we need here. I don't know how many students we have in this room, probably about 60, roughly half the class. So how many students do we need to get to agree to something to know that we have a quorum? Because the people at home, you know, they're already partitioned off. We don't care what their values are. If I have 60 students in this room, how many students do I need to get to agree to know that I'll only have one valid outcome? Right, 31. That's why we tend to use odd numbers, because it's just easier to reason about it. Turns out that 60 divided by 2 is 30, but that's not a quorum because that would give me 50-50, and I have to have one more than that. So 31. If 31 of you agree on the outcome of an operation, the fact that the other 29 didn't even know the operation was happening doesn't matter. Now, on the flip side, what that means is when I want to reconstruct that value, I have to find out from 31 of you what you think the value is. And you either know the value or you don't, but I'm guaranteed that one of you will know the value. And if only one of you knows that value, it had to have come from the quorum. Like, wow, that's pretty cool. So you mean I could have I don't know, the building collapses and half the classroom minus one disappears in some sinkhole, there's one of you who knows what the answer is. At least one. And now we can recover. But think about that. Okay, there's only one. I'm only guaranteed that one of you knows, so I may have to query all of you. Well, the rest of you should say, I don't know what the value was because I wasn't part of the quorum. So as soon as you find someone who says, I do know what the value was, now remember, we're assuming nobody's lying here. I was part of the quorum. I do know what the decision was. And you can trust that they are participating because everybody's telling the truth. And just to screw with your head at the end, we'll actually throw in the case where some portion of you are lying and how much lying we can tolerate. So any decision made by one quorum has to be part of every other quorum that could have been in there in the system. So we only have one value. We couldn't have two different outcomes. It doesn't sound really complicated. I mean, I wrote this slide and I was like, this actually makes it sound pretty simple. Well, I gave you the simplest of cases here. I said I'm just going to give everybody an equal weight here. In fact, when Dave Gifford proposed this in 1979, it was a long time ago on a planet far, far away, what he did was he used readers and writers, and he gave them weights. So it was weighted replication. So you could give individual nodes, individual participants, different weights in the system. But he said, as long as there is an intersection between the readers and the writers, you will always end up with a quorum. And the intersection was based on that weight. So he was giving a very general approach to it. What I like about this description is that it captures the idea that it doesn't have to be a reader-writer model. And part of the reason for that is because I said, there's this interesting work that was done fairly recently. It in turn is based on some work that was done 30 years ago about organizing your nodes in a matrix and requiring that in order to have a quorum, you need to have entirely own one row and at least one member in each column. And the reason that you can form a quorum from that is if you own one row, no one else could, and one entry in every column, no one else can own one row that has a different value. Because if they owned one row that had a different value, then that would violate the fact that you owned one value in each of those columns. And what's really fun about this is it means that you can have very small minority quorum. You do not need to have a 51% quorum. 51% is easy to reason about and it's easy to start with as an example, but then you say, yeah, but you know, hey, if you organize things correctly, you could come up with something more clever. When I saw the crumbling walls paper, and somebody pointed it out to me years ago, I looked at it and I said, that looks like a data center design. I get all of the nodes in one data center to agree on the outcome, and then I just have to get one node in every other data center to agree on the outcome, and I'm done. I have a quorum. I cannot have any other possible outcome. That actually makes kind of cool sense. I don't have to wait for all these very expensive messages to propagate through the system. I only need to get one of those nodes from the other data centers to agree, and I'm done. That's a pretty cool efficiency hack, isn't it? The things where I do depend on getting everybody to agree are the cheap ones, the ones that are close to me. And the ones where I don't need everybody are the expensive ones because they're far away from me. Heidi Howard in 2019 published a consensus protocol called Flexible Paxos, which is based on Paxos, but it is based on one of these alternative definitions of what it takes to create a quorum. And as far as I know, no one has actually implemented a library to do that. So my crazy idea was, if you want to do something interesting that might have legs, build that library, do it in Rust. Rust has this really cool package that somebody pointed out on Discord that allows you to do You can build a model. You can have a model checker built into your Rust code. Now you got a library that people look at and go, ooh, it's using really cool new language, it's using Rust, so I'm all au courant. And this has a really interesting feature set. Wow, this is kind of cool. You could be living on the cutting edge. You don't have to do that. It's a lot of work. You're probably going to do it wrong. But everybody else is going to do it wrong too. The goal here isn't to produce something that anybody else is going to use. It's nice if it happens. The goal here is for you to learn more about the right thinking patterns. How do I think about these problems? If you want to read more about quorum, I found a couple. The second paper is one that I ran across. It's fairly recent. It's an archive paper from earlier this year. And the first one is 1979. Weighted voting for replicated data. Super, super important paper for distributed systems because it provided us with a very clear model for how we don't have to have complete agreement amongst all of the nodes in order for us to be able to reason about what the outcome of a distributed transaction was. The read-write quorum systems made practical. I liked it because it has cool pictures. And if you like pictures that show what quorum, what a quorum is in these various different ways, it's a good one. Ooh, pretty pictures. I don't have to even read the text. It's a win. As long as the system can continue to construct a quorum, we will be able to continue using that system. That helps us meet our availability goal. Since we have this intersection property that says we can only have one outcome, and it doesn't matter which quorum we look at, we're going to find the outcome, we have our consistency goal met. Okay, so we've got consistency, we've got availability, and we're dealing with potential failures. So what's the price that I'm paying for this? It's complex as hell. Just thinking about this will make your head hurt. And if it doesn't make your head hurt, you're either very strange or you're not thinking about it right. Or maybe both. One of the complications in this consistency model, and I did touch on this before, now it's in text, this doesn't mean all the nodes are up to date. A big part of the complexity in these distributed consensus algorithms is, how do I catch up? How do I get up to date? Because I may not have been a part of the quorum that made that decision. How do I find that value? Each of the protocols has a mechanism for recovering that state. It can be explicit, it can be implicit. Often it ends up being designed in to be as efficient as possible. So for example, in view-stamped replication, you find out that a value was accepted because the leader sends you another proposal. And in our system, when the leader sends a new proposal, in the view-stamped replication system, when the leader sends a new proposal, it automatically acknowledges the previous proposal. But what happens if there is no new proposal to send? And view-stamped replication is very pragmatic about it. It says, well, we're going to wait for a little bit, and if nothing else comes in, we'll just send the message telling you that there was a decision. And now you know what to put in your log. Now you know what to do to your database. And one of the lectures that I linked to is the view-stamped replication lecture, which I really liked because it walked through recovery in a situation where one of the two nodes that was part of the quorum that made the decision failed, and the other node that did not participate in that quorum becomes the new leader and has to recover the state. It has to learn what that value was. And it walks through that and explains how you know that. And it's because of this intersection property. Consensus just means we get a set of resources, our nodes, our databases, whatever you want to call them, to agree on a value. Just one value is all we actually need to do. But it's not very hard for us to generalize this and to say it could be a series of values. getting from one value to n is an exercise left to the reader, right? So if all you have is one key in your database, that's your one value. Now, multiple keys in your database, then each of the operations may mutate one of those keys, or it may read the contents of one of those keys. It's the same process. We're just simply trying to agree on what that value was. When we do log replication, in essence, what we're doing is adopting a series of values that we put into the log. So it is the log that we replicate. The value that we agree is what's the next entry in the log. And you can make that really simple or really complicated. The benefit of having a log that is replicated is if we feed this into a state machine, we expect we will get exactly the same output. That's kind of the point of using state machines. Start with the same initial condition, feed it the same input, we get the same output. Doesn't matter whether we do it here or we do it on Mars. So, okay, well, the state machines we can replicate at the beginning of time. You install the software on your server, it's exactly the same software you install on the other server. All we have to do then to keep them in sync is to replicate the state of the log. Now, we could do that in a batch style, like once a day. I just simply take the log and ship it to some other machine. That means that if there's a failure while I'm working on that, I'd lose that data. That's kind of the backup model, right? When you actually back up a computer and take a tape off-site. People still do that. Tape is super, super cheap. But it doesn't provide you with the ability to rapidly recover. And what we want is georeplication. Well, I don't really want to have to send my tapes from here to, I don't know, some weird data center under the ocean in the North Atlantic. There's a Microsoft Azure data center in the ocean. It was mostly a gimmick, but there actually is one, and they do actually have data stored in it. Fine. I'm obviously not going to be taking tapes there, am I? I'm going to have a network cable that's taking signals to it. I'm going to ship stuff to it. We say it's consistent because I get the same output, regardless of where I replay that log. That's all we wanted to achieve in the first place. All we have to do is agree on what are the entries in the log. That's our value we're agreeing on. You just do it over and over again. Broadcast protocols have been around for a long, long time. This is where you just yell at people. Hey! What's for dinner? And then everybody yells back. I don't know, I'm not hungry. Or whatever. There is no guarantee as to the ordering of those messages or their arrival. You heard me pretty much instantaneously because we don't have the ability to perceive the small time differences that it took for that to get to you versus the person in the back of the room. And the speed of sound is much lower than the speed of light. And what is it? The speed of an electron in a copper wire is about 2/3 of the speed of light in a vacuum. Roughly, like that. We don't have any guarantee for message ordering. And we've got the troublemaker up here. You send the message to him, he holds on to it for a while, then he sends it tomorrow. Yeah, I'll forward it tomorrow. Fine, not a problem. So you have no guarantees as to the ordering of these things. That's one of the downsides to broadcast. Most of the time, broadcast actually works really well if it's like on a local network segment and there's nobody who can hold and forward the packet. Now the propagation delay is really just down to the physical media on which the packet is sent. But of course, we don't have shared media networks these days. Everything is star topology. So I talk to a piece of equipment and it resends that message out another port. So there are some small latency differences, but not large. It's like all of us being in the same room, you don't really notice them. You don't have to pay attention to them. When the messaging becomes from here to the Mars, or here to the moon, or here to you in your seat, there's a much bigger difference. And that latency becomes a much bigger deal. Well, can we make broadcasts more robust. And the one mechanism for doing this is this atomic broadcast. Petrov talks about that. It is actually used in Zookeeper atomic broadcast, but in fact it is based on some very old work from the project called ISIS. I had to check and make sure because there's been a couple of projects called ISIS, but it was the one I thought it was. And the idea behind that now is called virtual synchrony, but it was based on this original work called ISIS. It's a reliable broadcast protocol. The order of delivery is identical. All the messages arrive at everybody in exactly the same order, and therefore we have ordered our log, haven't we? Now we can just broadcast our log, and life is good because everybody gets the same exact log, and we know that our replicated state machine will come to the same conclusion. And it's all or none delivery. Either everybody gets it or nobody gets it. Can you think of anything that guarantees kind of ordering? You ever heard of this really wacko protocol called TCP? TCP guarantees the order of delivery, doesn't it? And it does that on an unordered network. So we know it's possible. We just need to scale it up a little bit. One of the things that I did when I worked for David Chariton many years ago was we built a transport protocol that allowed multicast. So we had reliable multicast capability, which is very interesting, kind of cool. And multicast is, broadcast is a specific instance of multicast. Multicast means that I send a single message and it goes to multiple recipients. And I thought it was interesting because Chariton actually didn't like this model and has an SOSP paper from the 90s criticizing this model that then led to refinements of the model, and that's how we end up with virtual synchrony. So people were like, well, this is all we need to build reliable and robust distributed systems. And he and somebody else, they wrote this paper, and it basically said, you know, it sounds like a really good idea, but it falls apart. Pragmatically speaking, we can use this in environments where the rate of change is very low. Zookeeper is a configuration database. It is replicated. When you change the configuration, you want everyone to see the same configuration. But configuration doesn't change very often, so something like an atomic broadcast protocol makes sense. You can go look at Zookeeper. Even though it's very simple conceptually, the implementation details are a lot more complicated. It is a critical part of Zookeeper and how Zookeeper works, how it maintains configuration state. Well, then we get our crazy clock dude. Got to do one better than Knuth couldn't do a good enough job of building a typesetting language. Leslie had to come along with a macro package that ran on top of TeX. That's how we get LaTeX. Anybody ever used LaTeX? You're CS students, so it's kind of one of those things that they inflict on you. Everyone else in the world will use Word. I can tell you that in systems in particular, submitting a paper to a conference that was written with Word is usually frowned upon. Not officially frowned upon. Just like, couldn't even bother to use LaTeX. It's kind of like people who look at you and say, what, you're using Emacs? No, my gosh, you're using VS Code. No, that's not the right way to write code. You use VI. And of course, in the VI days, all people know you use ED. Like, ED? ED, what's that? Ever heard of SED? Well, SED was the stream version of ED. Literally, you could send scripts to these things, and it ran this little command line editor. You've never had a greater pain than using a command line editor to edit a file. It's miserable. You have to tell it what line you're editing, and then it shows you the line, and you can edit it. Okay, great. We've come a long ways, but at any rate. So Lamport comes along, and he's done fixing the world with macro packages in TeX. Lamport comes along and he says, I'm going to talk about priests and olive contracts and ledgers. And he wrote this paper called The Part-Time Parliament. And it was sufficiently obtuse that he submitted it to a journal. They got kind of mixed reviews on it, and they never officially rejected it, and they never officially accepted it. And so like 7 years later, there was a change in editorial management, and somebody said, well, we should probably deal with this paper. And they accepted the paper. So the paper was published in 1998, but it was actually submitted in 1991. And honestly, it's the paper you want people who are not computer science people to read. Try and explain consensus to them, because it explains how the decision-making process works. And after seeing all of the papers and reading them last term, all these different papers on consensus, I came back and I said, now I know why Lamport wrote it that way. He wanted people to step away from their computers and say, what is the problem we are trying to solve? And from that perspective, it's a great paper. From the perspective of trying to figure out what the heck he was trying to tell us, it's a bitch. People read that and go, I do not understand what he's talking about at all. But it's there. You have a question? What was the state of consensus algorithms before Paxos? Well, okay, so we basically had read-write replication, weighted read-write replication. And in 1988, Oki and Liskov published ViewStamp replication. So if you actually look at ViewStamp replication, it looks an awful lot like Paxos, except that well, it looks kind of like multi-Paxos, except that the leader election is very different. I mean, I'll give credit to Lamport. He solved the leader election problem using the same protocol that he then uses later to say, and this is how we're going to replicate logs, or this is how we're going to replicate multi-variable state. But he said, I just want to agree on one thing. Who's the leader? And he came up with a mechanism for providing us with a protocol that does actually choose a leader. That's the one value he's trying to decide. That's it, just one value. Why do we want a leader in the first place? Well, why don't I describe to you what Paxos does, just for the simple basic Paxos case. Anyone in this room has the ability to suggest a leader. And in fact, what the protocol says is they suggest themselves. Hi, I'm the best one. Vote for me. I should be the next leader. Okay. Well, how do I distinguish the proposals? I mean, what I want to do is I want to have a sequence number, don't I? But I don't have a global clock. So how could I construct something that kind of works like a global clock in terms of arbitrating the ordering between these? And what he said was, we're going to take our ballot space and we're going to basically divvy it up amongst all the nodes that can propose a value. Okay. And it's sparse. So in other words, it's sparse, it's interleaved, and when you first think about it, I mean, okay, fine. So if I have 6 participants, I give you 1, 7, 13, and I give you 2, 8, 14, and you get 3, 9. So you can see how you can divvy that up like that. And so what happens is, when you first send your first proposal out, you say, whatever your first number is, 1. This is my proposal number 1, and I vote for myself. And then other people receive that proposal, and they say, have I already told someone else I will accept their proposal? And if the answer is yes, then was their proposal number less than this proposal number? And if the answer is yes, then I can say, well, I'm going to accept this guy's proposal. So it will accept a higher numbered proposal. Now, if everyone sends their proposals out at exactly the same time in this scheme, it doesn't converge very well. This is one of these interesting cases where Lamport basically exploits the fact that in the real world, things don't happen simultaneously. Now, in the actual Paxos Made Simple, which he wrote later because everybody complained because the part-time parliament was non-understandable, he actually says, You want people to choose random times before they send a proposal out. And that's a big deal for somebody like Lamport, because he's a mathematician. And this is not a mathematician's argument. This is well, if you want to make this work in the real world, you're probably going to have to stagger your proposals so that it gives other people time. So you're the one who sends the first proposal. Nobody else has sent a proposal out. If your proposal gets to a quorum of the acceptors, they'll send you back a message that says, I'm prepared to accept your vote. And as soon as you get a quorum, let's just keep it 51-49, you get more than half the vote, you say, I am now the leader. And you send out a message that says, we have agreed upon a decision, and that decision is, I am the king. And since nobody lies, everybody else says, okay, now you're the king. That's how Paxos elects a leader. If you send a message out and you don't get a majority of those votes, then someone else sends a proposal out, and they will eventually send that message that says, I am the king. And this is how we're going to construct our quorum. Because we now know that more than half of the nodes agreed to that proposal. You have a question? Yep. No, that was the whole point. They have to have different numbers. Their numbers have to be sparse and interleaved. Well, sparse, their numbers have to be interleaved and ordered, right? So I have to be able to take two proposal numbers and compare them and come up with a result. Now, what's interesting about that is they call them proposal numbers, but in fact, when you actually read the text, usually what they end up doing is turning them into strings. So like you'll embed the information about the server as part of the string, and that's how you can distinguish them. Yeah, and that's why you don't want everybody sending proposals out, because once I send a proposal out, if I learn about a higher numbered proposal, my proposal's dead because I know I can't win. And so this provides, in essence, a shouting match approach. And that's why we don't want everybody shouting at the same time. We want people to take turns shouting, and we have to have a way of arbitrating the shouting. And when somebody shouts loud enough and everybody else shuts up enough, then enough people say, okay, I'm willing to let you be the leader, then it becomes a leader. Now, that is a very hand-wavy, intuition-based kind of description of how Paxos works, but it is pretty close to accurate. The formalism is very simple, and that's one of the things that it's clear from Paxos Made Simple, which is the second Lamport paper I didn't put a link up for. It is very clear that Leslie is kind of unhappy about the fact that this is like the simplest of mathematical statements, and you people do not get it. And you read that paper, and you just know he's annoyed. You can just tell. But he wrote the paper anyway, because the idea was really important. Okay, now we have a protocol that gives us the ability to choose a single value. Just one value. Well, that's not very useful, is it? How are we going to generalize this? Well, let's go back and talk about view stamp replication, which I will talk about in a second because it's also known as raft. We needed a leader. We needed to have somebody who was responsible for making proposals. The reason that this often is beneficial is because having one person shouting and everybody else listening is a lot more efficient than having everybody shout in general. There are exceptions to this. If one person, one node, is making the proposals and other nodes are then adopting the proposals, this fits into a leader model very cleanly. In view stamped replication, the way they picked the leader was by comparing the network addresses of the servers and choosing the server with the largest IP address. Hey, it was a tiebreaker. Lampport's just giving you a tiebreaker as well to choose that leader. Once you have the leader then puts a sequence number. Now we don't have to worry about having this divided up, comparable sequence number space. Now all we have to do is just say the leader gets to define what that number is. But what do we do when the leader dies? And it doesn't matter which of these protocols it is, they all have to deal with the fact that leaders can die. The leader stops working. I haven't heard anything from the leader in a while. I wonder if the leader's dead. Ping. I don't hear anything. Hey. And this is the Paxos model. Actually, it works in view stamp replication very similarly. I can say, I think we need a new leader. In view stamp replication, it's called a view change. That ring any bells? Hey, this is like Design Project 1. Design Project 1 has this view server, but it doesn't really explain to you very well what its function is. In view stamp replication, its function was to serve as the leader. It was just one of the nodes that was elected because of its IP address. What happens if we don't have comparable network addresses? You're sitting on a token ring and I'm sitting on Ethernet and we don't have easily comparable addresses, or you're on IPv4 and I'm on IPv6. So Lampport's approach to this doesn't have that particular problem. Actually, maybe that is a link to, I think that link is to Paxos Made Simple by Lamport in 2005. There's some really cool visuals of this, by the way, of how these protocols actually work. The graphical demonstration link there, slides. Literally, you can like poke values in there and watch the messages fly around as it's electing things. You're like, oh, this is so cool. Somebody put this into a web browser. And this is in turn based upon PMMC. PMMC is the paper that is actually used as the basis of the DS Labs projects. The leader fails. We call a new election. It doesn't matter which protocol it is. We have a mechanism for electing someone. Anyone is allowed to call for a new leader. Now again, this is not a Byzantine environment, so we don't expect that people are trying to do denial of service attacks by sneaking in here and doing nasty things. Otherwise, you just simply constantly be demanding a new leader. Sounds like the US. So, okay, fine. So we have a protocol, we have a mechanism. Call for a new leader. How does the old leader find out that it's not the leader anymore? It gets a proposal with the new leader's number in it. What is the number that we use there? It turns out that what we do in multi-Paxos, Lamport's solution to this, is we use the number that was assigned to the proposal to elect the leader. They call it the ballot number. So the winning ballot number becomes the identification of who the leader was. You'll see this called other things like epoch. What is the epoch? All it does is it says, and in the view server model, it's the view number. All it does is it says this is the state of the leader at the time this proposal was sent out. So what we've done is we've now taken the Paxos protocol and we've created a second Paxos protocol and we've linked them together by using the ballot number of the first Paxos protocol along with the sequence number of the second one. So we can distinguish what happens when the leader fails, or we think the leader has failed, and we call for a new election, we get a new leader. Now we can tell what the proposals are from the new leader versus what the proposals are from the old leader. Why is that important? The new leader may not know about all of the proposals that were proposed and accepted under the old leader's authority. But since we had a quorum, some node in the system knows what those values were. And it may not, if there were multiple ballots or multiple proposals under a single ballot, it may be that different nodes know. But we are always guaranteed that some node in that system will know all of the values, the aggregate will know all of the values that were adopted under the old leadership. So the new leader, as part of its recovery mechanism, has to have some scheme for finding out what the values were for the old balloting system. This is what distinguishes the protocols. This is where things get very different. When you look at how Raft does this, Raft has a very different mechanism for recovering that state. The new leader cannot propose new values until it knows it is up to date. It's just not safe to do that because I don't know what I'm doing. Now I have to reason about that. I just made a very large blanket statement, but in fact, if it's a key value store, why do we use key value stores? Because they're really easy to reason about in this space. If it's a key value store, I can actually propose a new value for an existing key. That's not a problem. As long as I know the order in which any other values that get presented have to be processed. But here's the interesting thing. I have a new proposal for a key, and then I find out that somebody else in a previous epoch, under a previous ballot, previous leader, the leader, that decision was made for the same key. I know that if I've already overwritten that key, I'm done. So the ordering is actually pretty easy there, right? Because I can order those operations. As long as I know the order of the operations, if I've applied a later update and I get an earlier update, I can just throw it out. Append is going to make your life difficult, right? That's why I say they put append in there to fuck with you. Because now you're dependent on the state of the previous operation. If all you have is put and delete, hey, you can reason about that. You can say, okay, well, if you deleted it before I put a new value in there and I get the old delete, I can just throw it away. That works perfectly fine. So this simplifies your work in thinking about how am I going to recover in my new leader. This is great. This is really simple. And then, of course, make your life difficult, we will put append. Append completely changes the problem that you are solving. So the simplest solution is don't put append in your key value store. It's not, as a general point of order, it's not really super useful. But in fact, when we replicate logs, actually what we're doing are appends. Think of that as the reason that we need to think about append is when we replicate our log, what are we doing to a log? We are agreeing on the next thing that goes into the log, which is appended to the previous log. So the new log is the old log plus the one new thing we've stuck on the end. So, okay, well, I guess maybe we'll have to think about append, but we could at least keep it to just the stuff that we do and reason about, and that will simplify our lives. And when you're designing these things, you're thinking about these problems, you have to keep reminding yourself, what do I provide to my external agent and what do I need to do for my internal processes? Keep the complexity on your internal processes, keep the external interface as simple as possible, your life will be a lot easier. The moment you start to dabble in complex state management with the external clients, it will become much more complicated. Have any of you ever heard of this thing called a SQL? So SQL databases actually allow you to do things like transactions, where you can do a series of mutations on the database that are wrapped up in a infrastructure that ensures atomicity and consistency and keeps it isolated while it's in progress and makes sure that it's durable once it's done. It's really hard to get right. It's important to get right, but it's really hard. And doing it in the general case is really challenging. Real databases actually have mechanisms for supporting this. And if you want to screw with them, I'm going to start a transaction today and I'll just keep it open for a while. oh, let's see, 6 months later, I say, I'm going to commit that transaction now. That's how you make database people's lives miserable, right? You keep these transactions open for long periods of time. You hope that the database doesn't crash in the 12-month or the 6-month period that you waited. Because if it crashes, it will probably just abort the transaction. That's the flip side, that if you keep a transaction open too long, we may just simply say, I'm sorry, we're going to abort that. So everything you think you did, it's gone. Paxos has a whole series of requirements. I don't want to get too much into these details. It's mostly about making sure that there aren't kind of useless systems to worry about. The only proposed values may be chosen thing means that this has to have been at least bivalued in its initial state. There have to have been at least 2 possible outcomes. Otherwise, it was already a univalent system and all of this work is completely pointless. If you knew what the value was in advance, why did you go through all this extra work to choose it? You can only choose a single value. That's the point is, no matter how many ballots we go through, in the end, we agree on one value. We know who the one leader is. Even if that leader could change, we know what that value is now. We've all agreed to it. When we talk about the recovery, in essence, we're saying, and this is how we're going to deal with it when our reality, we agreed that this was going to be the leader. Oh, our agreement broke down. We have a change of government, and we have to pick up the pieces and make things work again as quickly as possible. But we're going to maintain that illusion that we have a leader all the time, and the same leader. The queen is dead, long live the king, right? Our model is, we don't know the operational speed of these nodes. They can fail stop. That was the FLP model, was fail stop. We have fail restart, which is the real world condition that, hey, I unplug a computer from the network and then I plug it back into the network. I don't expect the computer will go back and completely be reinitialized to its beginning condition, which is what happened in the design project, right? When a primary dies, we just assume that it ceases to have any useful data on it. In a real world situation where we have these quorum going on, we have a quorum system, part of the reason that we're maintaining all of this state is so we can get them caught back up when the system recovers. So with the quorum, we know that we don't necessarily have complete knowledge, but we have a system-wide knowledge. At least one of the nodes in any new quorum will know what the outcome was of the previous decision. Messages can be slow, they can be duplicated, they can be lost, but they cannot be corrupted. We're going to talk about the Byzantine case in a minute, hopefully, if I can get through these slides. Like I said, too many slides, and I knew this was going to be long. This is the Paxos lingo. Just, if you really want to know more about it, it is in Petrov, it's in the Lamport papers. Pretty much everybody uses some variation of this. The worst part about reading these consensus papers is they all use different terminology, the same general concepts. He has proposers, acceptors, and listeners. Listeners in Lamport's Paxos model are your databases. So this is the interesting thing when you think about it. The proposers and acceptors are the decision makers, and the learner is the one who actually owns the state. And that may not be clear to you when you first go through this. We have to agree on the order of events. That's what the listeners and the proposers and the acceptors do. And then the listeners are the people who action that stuff. Oh, okay, now I know what I was supposed to do, and I'll go do it to my database. That's just the walkthrough. I've already done that. I'm not going to spend more time on that because I want to get to Raft. Yes, so it's pretty much view stamp replication. And there are some differences, but they are more similar than different. And I kind of feel sad for Ongaro because he took a lot of shit for this when he presented this at SOSP in 2015. And somebody said, how is this different than view stamp replication? And he'd never even heard of it. I don't know if it was that presentation, but apparently the first time he presented this work, he'd never even heard of Liskov's work. And he was the student. On the other hand, John Osterhout, his supervisor should have known. He would have known. He did know. So we elect a leader. The leader election here is network-based, both view-stamp replication and, view-stamp replication chooses based upon the network address. I thought that's what they did in Raft as well. It doesn't matter. You can replace it with a Paxos election protocol as well, and you end up with the same result. The reason that the Raft is considered to be a good protocol is because it was easier to explain to people. You're sitting there going, well, this is so simple anyway. I don't understand why this is so hard. People had a very hard time and still have a very hard time understanding Paxos. And it's mostly because the ramifications of the ordering and the racing ballots and the proposals and how you make sure all of these things work is conceptually, it's really hard to think about. We don't think about out-of-order operations very often, nor is it particularly simple to do so. I think that's the hardest part about this class. It's not that the material itself is difficult, it's that it doesn't fit with the model that you have been trained to. You think of everything as being sequential and being synchronous, and suddenly we throw like, oh, well, we're just going to randomly reorder things, or we're going to duplicate things, and we're going to have to send these messages around, blah, blah, blah. And thinking about that is hard. And that's the skill set, or a skill set, part of the skill set that I want you to leave with. That's why I think design is more important, because design forces you to think about it. I did get a piece of feedback from one student who said that he's taking 508 from Redo. And Redo had people do design theirs as well. And he said, but they didn't distinguish the design from the implementation. They did it all at once. And he said he really liked the fact that the design phase here was separated from the implementation phase. And I'm torturing you by making you implement somebody else's design. Not because I care about what you implement, but rather because I want you to understand what design can do when it comes to sitting there and trying to implement it. It can either make your life miserable, or it can make it really easy. And I suspect there's going to be a whole spectrum of that kind of outcome. Why am I doing it? Because you're going to end up doing a capstone project, and I want you to finally be motivated to actually write a good design, because you're saying, I don't have a lot of time at the end to actually implement this thing, so I better do my work up front when I'm designing it. And that's actually real learning objective here, is for you to begin to understand why it's better not to sit in front of the keyboard and pound your head into it over and over again. I mean, how many of you have spent many long hours debugging stupid little programs that you go back 2 years later and you look at and you go, why was that hard? One person admits to that. 2 people. Come on, be honest, people. Oh, I don't write code. Okay, fine. So there's some marketing people who snuck into this class. I don't know why. That's the joke in tech, right? Marketing people don't get bugs because they don't write code. And it's normal for you to go back and look at things once you've internalized it and you understand it better. You go back and you look at, it wasn't very hard. Why did I think this was? Raft has a nice little visualizer as well. That is actually the one that Ungaro built for it, and it's still there, and you can go look at it, and it helps you see the flow of messages through the system. And it's kind of cool, because these got little slider bars, and you can control how fast or how slow the messages are sent, and you can control the frequency of losing messages. Okay, so we started off with this premise for the others that nobody's lying, all of our messages are inviolable, they're not corrupted, blah, blah, blah. What happens when we lift that limitation? We end up with what is called Byzantine fault tolerance. Does anybody know the reference Byzantine? Do you know what it refers to? You're computer science people, so you shouldn't know any history, right? Because nothing existed prior to 2004. Right. And what was the problem with the Byzantine Empire? Not to bring politics back into things. Actually, it was because it was well known for people lying. If you study Machiavelli, I would argue that Machiavelli was teaching people how to re-implement the Byzantine Empire, which was people told lots of lies. They tell you what you wanted to hear. They manipulated you. And that's kind of the point. Once we decide that we're going to allow people to fake messages, to misbehave, the question becomes, can I still build a distributed system that achieves consensus in the face of up to some number of malicious actors? Why would anyone act maliciously? There's usually one answer that pops into your head, and it's probably the right answer. Why do people try to scam you? What do they want? Money! So guess what one of the biggest scams, distributed consensus algorithms is for dealing with money? Oh my gosh, it's like beating you guys to get you to do the obvious thing, right? Blockchain. How many of you have some Bitcoin hanging out in your wallet, right? I've never had more than 2 Bitcoin in my life, but I have had Bitcoin. I knew somebody who actually paid his way through his undergraduate mining Bitcoin on university computers. That was back in the days when you could still do it on a CPU. So that was like, 10 years ago or something. Yeah. In fact, that is probably the best example right now of why we care about Byzantine fault tolerance. But practical Byzantine fault tolerance is quite a bit earlier than blockchain. But they are solving essentially the same problem, which is how do we protect ourselves against malicious actors? In PBFT, what Liskov and her student at the time, you'll notice that name, these names keep coming up. It's the same like 6 people in this field, I swear. The system they came up with, they said if we assume that there are some number of bad actors, we need 3 times that number of bad actors plus 1. Gosh, this is just like what we had with quorum. So basically, for all intents and purposes, what I think is kind of cool about this is all the bad actors, we just don't care. Just ignore them and we have our quorum system. So the reverse way of thinking of this is I take my quorum system and then I add, so if n is, the number in my 2n, well, let's see, n plus 1 is my quorum. That's why I need 2n plus 1. I can have as many bad actors as I need in my quorum in the first place, minus 1. Okay, so now I can have 3, in this case f, 3f plus 1, where f is the number of faulting processes, Byzantine processes. We can actually do better than that. But this work is pretty interesting, and it doesn't require burning a small country's worth of electricity to compute on an hourly basis. Blockchain is an interesting solution to this problem. It solves a number of issues that people dealt with in the early 2000s around electronic cash. A guy named David Chaum did a whole bunch of work here. And then this serious paper shows up. We ostensibly still don't know who actually wrote it. And it's a quasi-academic paper. It's not like a formal academic paper, which defined Bitcoin. And its contribution really was to define a protocol for reaching consensus. It is a consensus protocol in a Byzantine environment. People have done work since then in blockchain, and they have been able to tolerate up to 2/3 of the network being filled with bad actors and still be able to come up with a valid consensus. Pretty cool, called Algorand. People work on this. It is real. So I wanted to tie this into some real use cases, and so I said, yo, chat, give me some examples. And then chat gave me some examples, and then I dug up some links from those examples, and I checked to make sure that the links that chat gave me were all valid. Surprisingly enough, they were. And I poked it on a couple of them, and I said, I don't like that example, and so I curated the list. There you go. So a distributed key value store, I picked Anna. ANA is a really cool distributed key value store that uses consistent replicated data types, CRDTs, which are eventually consistent data structures. And ANA scales from a single node all the way up to very large multi-node systems. Kafka is what you are using indirectly when you order your food. Does anybody order food for delivery? No, nobody does. Right. One person admits that they order food. So, you get on DoorDash, Uber Eats, Skip the Dishes, Fantuan. How many of you use Fantuan? There's this really cool place that delivers pizza with lobsters on it, and that's the only place you can order it through is Fantuan. But they all end up using something like Kafka for messaging, for order management, believe it or not. The friend of mine I was telling you about who cost the company $150,000, they use Kafka as well. They do streaming order management. It's a very commonly used framework, and that's a distributed message queue. It's a distributed system. Hadoop is old and ancient and crotchety and cranky, but people still use it, and that is just a distributed file system based on this thing called the Google file system, which always gives me pain every time I say the word file system. It's not. It's not. Redis, which is used for distributed object caching. Apache Zookeeper, which I've already mentioned, that's where the Zookeeper atomic broadcast protocol is used, but Apache Zookeeper is a more general configuration management system. Giraffe is distributed graph processing. It turns out graphs can get really big, so big they don't fit on a single machine, so we have ways of dividing them up and farming it out to a collection of machines. Stream processing system, Blink, one I don't know much about, but that's fine. Distributed load balancer. I actually checked that one out because that sounded a little dodgy to me. But in fact, HA proxy is still there, high availability proxy, so it does load management. These are all used in data centers every day. Many of the services that you rely on for all those apps on your phone. Anybody have a phone? You guys won't admit to anything at this point. Nobody actually orders food. None of you actually eat. I'm sure none of you poop. So, and clearly none of you are sleeping. But a few of you have a phone. How many of you picked up a new phone in the last week? Nobody's willing to admit that one. What were you running all those scams for? Oh, sorry, there are no scams here. And for blockchain, I actually picked Ethereum. Of course, that's the environmentally friendly solution these days for the last 6 months. Before that, it was also wasting a planet's worth of electricity, doing useless work. There you go. That was a lot of material to get through. I think the most important thing to walk away from this is understanding why consensus is based on quorum. What quorum is. It's just some subgroup of the deciding nodes that's large enough that there can be no other subgroup that doesn't have at least one member in common. It's easy to think about that in the split the class model. It's a little harder to think about that when we start doing two-dimensional. And I dare you to go do 3 dimensions, because I'm pretty sure that 3-dimensional could be really interesting. Think about, look at it that way and that way. But you could probably come up with some interesting themes there too. That's the point. Quorum allows us to get recovery. And recovery is the hardest part of this. It's when you sit down and you start thinking about, okay, the leader's changed, and I pick some poor podunk server that doesn't know anything about the state of the service, and I elevate it to leader. How does it catch up? That's when things get hard. You do not want to be doing this in front of your keyboard. You do not want to be debugging this logic and going, why is it not consistent? You want to step back from it. You want to say, hey, I just took the new, you're all 4th years. You remember when you were 1st years. I just took the new 1st year student and said, here, you're now the leader. What do I do? You get to explain to them. How am I going to get you to where you need to be in order to do the job? I'm guessing there aren't a lot of questions because we have 1 minute left. There are probably tons of questions. You can ask them on Discord. I do tend to answer questions on Discord once in a while. I am much worse at looking at Piazza these days. I apologize for that. I did check earlier today. There were no outstanding questions. And that's going to be a wrap. I hope you have a good long weekend. I know that I gave you something that's due on Tuesday, so you don't have to work over the weekend if you don't want. Or you could just carry a copy of Petrov with you and read it while you're sitting on the beach here. It's supposed to be sunny, at least tomorrow. Not warm, just sunny. And that is a wrap.